Here's a diagram of the 4 chambers of the heart. So let's name them to get started. So we've got the right atrium up here, we've got the right ventricle down here, we've got the left atrium and the left ventricle. So these are the 4 chambers, and blood is going to flow through all of them and then get out to the body. So to do this and to do this right, the heart has got to coordinate how it squeezes. And we know that the way that it kind of squeezes down is you have a cell, and that cell is usually negatively charged, and it will at some point become more positively charged. And we call that process depolarization, right? So depolarization is the idea of going from a negative membrane potential to something much more positive. And when you depolarize is when the muscle cell can squeeze down. So where does that begin? Let's actually draw it into our diagram. So if you were to look, there's actually an area here where little cells can actually depolarize by themselves. And that's actually quite unique because most of the cells in the body are going to depolarize when that neighboring cell depolarizes. So these are actually really unique cells because they're depolarizing all by themselves, and we call that area the sinoatrial node. Sinoatrial node, sometimes called the SA node, sinoatrial node. And the fact that they can actually depolarize by themselves, we have a word for that too. We call it automaticity. Automaticity. So it just means that they can kind of automatically depolarize without having a neighbor do it first. So once they depolarize, what happens after that? Well, when these cells depolarize, they're connected through little gap junctions to the neighboring muscle cells. And so they're going to start sending out waves of depolarization in all directions. And so it's almost like going to a football game and watching the waves start. You know, it just goes on and on and on. And so all of the neighboring cells are going to start depolarizing as well. And that orange arrow is moving kind of slowly, right? That depolarization wave is moving kind of slowly relative to how fast it could be moving if it went through a specialized band of tissue. So this band of tissue that I'm drawing, this blue band, is almost like a highway compared to that orange arrow, which is like a little road. And that highway is going to take that same depolarization wave over to the other side, over to the left atrium. And all of these cells begin to do the same thing. They start depolarizing as well. So you get depolarization happening both in the right atrium and the left atrium in a coordinated way. So it's happening all very, very evenly. And this band or bundle is called Bachmanns Bundle. So it's like a little bundle of tissue, right? So it's called Bachmanns Bundle. So now we've named 2 things, the sinoatrial node and Bachmanns Bundle. And actually, just like Bachmanns Bundle, there are actually a few more little bands of tissue, almost like little highways, that take that signal down to another node called the atrioventricular node. So this right here is the atrioventricular node. And the atrioventricular node is really the only major connection, I shouldn't even say only major, only connection in most of us between the atria and the ventricles. The atrioventricular node, and this is actually sometimes called the AV node. So the AV node is going to get this signal, and actually I didn't even tell you what that signal came through. This is kind of a generic name, internodal, just meaning between 2 nodes, tracks. And that's kind of the name for all 3 of them. So the signal went from the SA node through the internodal tracks down to the AV node. And there, kind of an interesting thing happens. So if you actually take a step back and look at the AV node, let's imagine we're now kind of focused in on exactly what's happening there. And to figure out what's happening there, I'm going to give you a little scenario. So let's say that you've got let's say a little timeline here, and that timeline is, let's say 1, 2, 3 seconds. 3 seconds. And your job is just to watch the atria and see how they contract. So you just watch the atria and you say, wow, I saw one contraction that happened right there, and one contraction that happened right there. and one contraction that happened right there. So the atria, as they get the wave of depolarization, are contracting now 3 times in 3 seconds. So for the atria, you saw 3 contractions. Now you do the exact same thing, but you do it for the ventricles. So for the ventricles, you kind of just keep an eye and you watch, exactly what happens, and you notice that there's a contraction of the ventricles there, and again there, and one more there. So both the atria and the ventricles are both contracting the same number of times, but the unique thing is that there's like this little delay between the two, right? They're not actually contracting at the same moment in time. There's this tiny delay, and if you measured it, it would be about 0.1 seconds. So just a tiny little fraction of a second. But the reason that there's that delay is due to the AV node. So one of the kind of interesting things about the AV node is that it creates a delay between the atria and the ventricles. So delay between atria and ventricles. And the reason that that's really important is that if the atria and the ventricles were actually contracting simultaneously, then they would actually be squeezing blood against each other. They would be actually doing work that wouldn't actually move the blood in the right direction. So by creating the delay, the atria can squeeze, the blood can move from the atria to the ventricles, and then a tenth of a second later, the ventricles can squeeze, and then the ventricles can move that blood onwards. So the reason for the delay is actually to make sure the blood moves in a coordinated way through the heart. So now this signal has delayed by a tenth of a second, but then it continues on, right? It continues on, and it goes to a little area right there, and this is called the bundle of His. Bundle, kind of funny names, I know. Bundle of His. And even though it's spelled H-I-S, you don't say his, it's hiss, almost like what a snake does. And then it continues from the bundle of His through one track down here, and this is considered the right bundle, and then it goes through the left bundle. And actually the left bundle splits. There's like a forward part that goes up to the front and a part that goes to the back, and I'm going to draw the back part kind of dashed like that. So this is called the left posterior, because posterior means back, posterior fascicle, and this is called the left anterior, because it's coming forward, anterior fascicle. And you got to kind of imagine that it's going forward and back, because obviously in 2 dimensions it's hard to show that. And then this is just called the right bundle. And actually, just so you're not ever mistaken, this part right here is called the left bundle, where it's still combined and it's not broken into the 2 fascicles. So you have the left and the right bundle, and then the left bundle splits again. And then all the fibers get really kind of split up here at the end. And these are called the Purkinje fibers. And it happens on both sides, the Purkinje fibers. And from this point, basically, the electrical signal can kind of dash out in all directions, right? So you can finally get all the muscle cells involved. So up until now, it's been part of the electrical conduction system, meaning these are all the highways, but now you have all of the waves of depolarization going through all the little tiny roads. And I'm using the idea of roads and highways just to point out the idea that through the electrical conduction system, the signal moves really fast. And when you get down into the muscle itself, then the signal moves slightly slower. But you can see that that's important because that's the only way to get all of the muscle cells on the same page. So this is how the electrical signal moves from the SA node all the way through the electrical conduction system so that the atria are beating together, and then goes into the AV node where there's a little delay, and then down into the ventricles where again the ventricles are going to beat together.